Recording in progress.
So I guess welcome everybody again after the break. I hope you all enjoy your break and take it easy. So I guess we could start summing up a little bit of section 6 that maybe we don't remember quite much. Just a recap. And so to see where we are heading. So section 6 was about Cartier modules. And a bit about centers of purity. So I guess this is the key way to understand regularity here. So we had a Cartier algebra. Remember that this is going to be this greatest ring over the natural numbers. And what is the condition we ask about it? Well, we always want that the degree 0 piece is R. And this is going to make every single piece here CE as an R module. So CE becomes an R module, but all we want is that, so it's a bimodule, so it's going to satisfy this property. Right? So for all kappa in CE and R in R. Right? And so there are essentially two types of examples here. What are the examples? We can take a module R and we can define this full Cartier algebra, which is going to be given by taking all possible Hom sets. Here, right? And you can take, this is the full one, and then you can get creative and cook up all sort of sub-algebras inside there that are of interest. Or the other typical important example is we cook up C to be the free Cartier algebra generated by one single element kappa in degree. Well, you are also free to cook up the degree you want, but very standard. We cook it up to be in degree 1, just for convenience, I suppose. Because so not necessarily. Okay. So these are the two standard examples of the Cartier algebra. And so, well, this concept of series is not so important. What is important is the notion of a Cartier module. You know, it's a module in which C acts, right? So remember that a Cartier module, it's gonna be simply a module such that, well, a Cartier C module, right? A Cartier C module is going to be a module on which C acts. And what is this action thing? So an action C is just a homomorphism of Cartier algebras, a homomorphism of Cartier rings from C to, well, it has to be greatest, right? So to the full Cartier algebra of M, right? And this is just to say that every single kappa here in degree CE is going to be able to act on M, right? Kappa is going to be a map. It's going to become a map from here to here. And one of the most important examples is when C, again, is this free Cartier algebra. We should give this a name. I'm tired of writing this down all the time. But if C is this principal, that's what people say, Then a Cartier module is nothing but the choice of a map phi, or kappa, let's say, from here to here. Okay? And more fancy Cartier algebras are just, fancier systems of actions considered all together. So, just as a remark that I don't think I have made, sometimes people call a Cartier module the following. If you go and look at the literature, people sometimes just write this. They don't put the Frobenius push forward here, but then they impose a different condition. Well, they impose the exact same condition here, right? But then they say such that R kappa equals, I guess the condition is that kappa of RPM equals R kappa M. So a Cartier module structure on M is this map. It's a map from here to here that is additive, it's additive. It's a map of abelian groups. It is not R linear, but it satisfies this relationship. And when people write this, people often say that this is a P inverse linear map. Okay. That's very common in older literature. But the modern or the contemporary literature is converging to this notation to say that it is a map from the push forward time to M. So we have this notion of Cartier module, and this is sort of the right setup to talk about F-singularities, because F-singularities are better understood as properties, or as module theory properties of these modules. So what did we say, for example? So the first thing we saw is that the category of Cartier modules, if we fixed, let me move a little bit, if we fixed C, right, and maybe we look at Cartier C modules, the important ones are kind of dumb modules, so we can just localize them and say that they are 0, and then give the category of Cartier crystals. Cartier C crystals. And this is a localization. This is a localization process of the third subcategory of nilpotent ones. Right, so if you have a Cartier module such that it is killed by sufficient large degree, then you just declare it to be 0. Right, like what you do is that you formally invert maps to say that that is isomorphic to 0. So this may look like fancy, but it's very formal, and it's just pure algebra nonsense. There is no reason to be scared of this. Then what we saw is that an object here has finite length. And that's the most important structural result about Cartier models. They are very finite objects, right? So how do we do this?
Excuse me, here the C is an R module.
C?
I mean this
CM.
Yeah, the C over there.
Yeah.
And then, but when you take this Cartier crystal, is it still an R module or what's? You say it's a localization, so you take a C module, so it's an R module in particular, no?
Yes, all Cartier crystals.
and then when you say the crystal, so this is an equivalence class. I mean, when you say you localize with respect to this nilpotent,
Yeah.
so an element there is an equivalent class of objects, right? Because it's
no, in this localization, actually, the objects remain the same.
The objects remain the same.
Yes,
and so it's only the arrows? Or? Yeah,
the arrows are different. So the arrows are so that essentially what you do, well, it's formal, but what you do is that if you have two Cartier modules, meaning that they are R modules in particular, but you have an action of Z on both of them.
Mm-hmm.
And well, the map here is compatible with that action. So if the kernel, so we saw that this is in particular an abelian category, so the kernel and co-kernel also have the Z module action. But if the action is nilpotent in here, meaning that there is a sufficiently large power here, we call it like something like this, of this ideal, such that it is zero, then what you do is that formally you call this mapping variable. So you construct a morphism, you just add it, you just say that it exists. You know, in the same way when you invert an element in a ring, you just say, well, this element now has an inverse, all of these other. So you do a similar thing, and in particular, these two things become isomorphic. That's what you do. You still have the old arrows, but you add a whole bunch of more.
I see. So the objects are the same. They're still Cartier module. It's the same Cartier module.
Yeah.
But only is that the maps are equivalent classes of maps, or not. Or is so. Yeah, because you're saying two of them are equivalent, or I mean, when you localize. I'm acquainted with this localization procedure for this category or this
the right categories?
Yeah, the right category.
Yes,
it's like in the right category.
Yeah, it's a similar thing. So yeah, formally speaking, now the arrows are gonna look like roofs. Maybe that's what you have seen. So how is it? So now a map, it's gonna be a roof. You have to add an M prime, and a map is gonna look like a roof.
You're allowed to take roofs, but
and so, but there is a particular which one has to be nilpotent. This one here has to have kernel or kernel being nilpotent. And a map is going to be an equivalent class of roofs. So in the sense that you are going to say that two roofs are equivalent, if they are dominated by a third one, and so on.
So does it mean that you're throwing away the nilpotent part of?
Yes, the process is made so that nilpotent objects now are isomorphic to zero.
To zero.
Yes.
Is there some zero? Is there some reason why nilpotent? You want to get rid of the nilpotent part? I mean, one might think that you're losing some information there, no? Why should you get? Why should one be interested in doing this localization procedure?
Well, one reason is that because then you can make this statement. Yes, that you see that the category of Cartier modules has finite length up to nilpotency. So the point is that, well, one reason is that if you have a chain of Cartier modules, you want to say that it stabilizes on both sides, but you can only say that up to nilpotency. And so if you localize, that's what my point. If you do that localization, the statement is just true on the nose, without having to say, oh, up to nilpotency. There are several reasons actually. The main reason is that the theory becomes very satisfying.
Is what?
Very satisfying. Once you get rid of nilpotency, the statements become very nice. So one example we saw is that if you have a module M, so it contains this stable module. We call it like this. This is a Cartier module. And so it admits this submodule. This is literally a submodule, but this one is a pure. And the quotient here is important. So for many reasons, you want to replace this by this. Okay, and so that's what you do. In the category of Cartier crystals, M and this are isomorphic, and therefore you can always deal with a pure Cartier crystals. That's one of the essential reasons why this is also useful. Because if you go to the literature, the classic one, you always see a purity being an assumption that is sort of indispensable, like it's just there. But something else, well, you could rather just say, okay, I'm just going to work with Cartier crystals, and you can say that they're all pure. Because you can always, this it is isomorphic to a pure one. So in a sense, like this localization process is also explaining why purity is everywhere. Because all Cartier crystals, which is what matters for the theory, the theory is very stable under crystallization, so to speak. And therefore everything becomes, just better behaved. But this is not something actually we are using too much in this course. It's just satisfying because, well, actually something what I wanted to say is like this finite result is a consequence of the existence of test modules. And actually the test module itself is an environment of the crystal. Two Cartier modules that are, when people say that they are nil isomorphic, if they're isomorphic as Cartier crystals, meaning that kernel and co-kernel of nilpotent have the exact same test module. So test modules are certainly, among the most important objects in the whole theory. And what you realize is that they are actually invariant of the crystal, not the module itself. So that's another reason why you want to get rid of nilpotent ones. Because nilpotent ones, as far as the theory is concerned, are the same thing as zero modules. And so it's convenient to, to get rid of all the trash and just work with what matters, which are the crystals themselves. And there are many more reasons, actually. For example, the Riemann-Hilbert correspondence works with crystals. So I think you may have known about the Riemann-Hilbert correspondence in characteristic between D modules and certain purposives, but there is this correspondence in positive characteristic which works with crystals.
Okay.
So yeah, in a sense, it's just the theory keeps throwing in the face that the crystals are important objects. So it's just useful just to get rid, just to work with them. Even if you don't have to, the statements just become very clear or satisfying like this. Yeah, that's it.
But I mean, you're using the analogy with linear maps. I mean, when you say you get rid of the nilpotent part, is like only considering the semi-simple part.
Yeah.
But in some sense, you might lose some information when you do this. I mean, okay, I agree with you.
But
numbers are better and whatever
you may lose it. You're right. You're right. You lose it. But the theory tells you that this is information that is fine for getting about. It's not important.
That's a matter of taste.
Yes, it's true. It's true, but no, it's true. You're losing information.
You lose some information. You might say, well, this is useless information. But in mathematics, usually there are no useless information.
In a sense, actually, it is. So what happens actually is this. This is something I can say when I move to the other side. So.
No, it's okay. It's okay because I'm particularly interested in something which is important, and then here you're throwing it away.
It's a very good point. I think this is what happens actually. It's more of a meta statement because it's just based on examples. So what happens is that positive characteristic essentially is divided in between wild behavior and tame behavior. Okay, and so the tame behavior is whatever you expect to happen from characteristic zero intuition, right? And the tame behavior is this semi-simple mathematics that you may be considering, and the important ones is where all the bad things happen. All the pathologies, all the wild things, all the wild arithmetics, it's there. It's some sort of nilpotent behavior. So what this is sort of suggesting is that the F-singularity part is concerned only with the tame behavior. And actually F-singularities behave as singularities you may expect from characteristic zero. That's why there is a strong analogy, with the singularities of the MMP. And any other behavior you may see based on potency and things like that are pathological behavior, or I don't like to call it pathological. I think that's very discriminatory because it's just, if you come from characteristic zero, you may call it pathological. But it's just like, new behavior, new problematic behavior. But F-singularities, by their own nature, have nothing to do with that. And actually what they do is that they get rid of it. Like, you don't see that. And therefore, that's why your statements work.
Mm-hmm. Okay.
And all the counterexamples, for example, of Quadraro vanishing and all that is important behavior. Mm-hmm. And for example, you may have heard that if you work with F-singularities, like you get word from vanishings for free, like Quadraro vanishing holds for pure things almost for free. Because I think morally what you do is that you just got rid of every nilpotency altogether. And so you don't have any pathologies to worry about. Yeah. So what this is, this is the point. What this is telling you that F-singularities ignore all nilpotency, and therefore things work. Yeah, I think that's the moral of the story. And actually, what I like to do in my own research is to make this sort of thing explicit. Or that's something I enjoy, like playing between tame and wild, and using F-singularities to express what is tame, and the lack of F-singularities to express what is wild, and things like that. No, it's a wonderful question for sure. The other day, or before the break, we were talking about this finiteness thing. One of the motivating reasons for that is that this finiteness is equivalent to the existence of test modules. Okay. So if you have a Cartier module, let me call it like this. To this, you can attach a test module. Actually, the test module is an invariant of the crystal. In other words, for example, the test module of n, c is the exact same module as the one of it's a pure, submodule. And it is defined, well, it is inside here. It is a submodule, first of all. Cartier submodule. And the property it has is that it is the smallest Cartier submodule that agrees generically, with this one here. Meaning that if you look at the minimal primes supporting this module, the canonical inclusion that you have becomes an equality. Okay? So it has this strange definition at this point But this definition, at least, was very well suited to get these finalized results. Okay? That was the whole point I wanted to make, that we have these test modules that may look slightly bizarre, but they give you this existence, the finalized results. I don't know if I wrote down this example, but if I didn't, then I should put it in the notes. Maybe I'll do that later. So for example, the most important example to consider here is a test module that is going to become an ideal, right, of a pair like this. In this case, this was the smallest ideal. Well, now it's going to become non-zero ideal. No, not zero. The smallest C ideal of R. What is a C ideal? Look, before the break, these things, we define them as a set of ideals of R. Let me call the ideals of R like this, such that they are stable under the action of C. So in other words, another way to say this is that these are the ideals such that the canonical map from here to here is a map of Cartier module, maps of Cartier modules, Cartier C modules. And what was the main application we had before the break? That this set is finite. Oops, sorry. So this set, I just wrote it here, is finite. That was the main application, assuming test ideas exist, right? So these are all ideals of R that are compatible by the action of the Cartier algebra in question. And so another way to say this, well, let me give reinforcing ideas, is that whenever you have a kappa, it descends to the quotient. That's all this means. Right? So if you have these commutative diagrams, that's equivalent to say that the canonical quotient is a map of Cartier modules. That the action of kappa on R descends to R modulo A in a compatible way with the quotient, right? So, what am I saying? So we saw that this is finite. It is closed under some intersections, and also closed under primary decomposition. Right? These are things we saw. In particular, all of these things together tell you the most important ones are the prime here, right? And so then you can define this is going to be this smallest ideally here. Well, if R were a domain, I just need to say that it's not zero. But let me say the smallest of R that avoids all minimal points. Okay, so since zero is always an ideal that is going to be compatible, right? So are all the minimal primes. And those are always trivial. They are there no matter what. But the test ideal is this magical one that avoids all the minimal primes. That would be the translation of the situation. Because what is the thing? Like, if you have an ideal that avoids all the invalid primes, it is automatically equivalent, it's equal to R generically, right? Think of a ring that is a domain. If you have an ideal and you localize at the 0 prime ideal, then that ideal that you started with becomes R, right? This is the thing that when you localize at the prime, you lose all other ideals that are not named. So yeah, this is the most important example to keep in mind. Okay. Well, I was supposed to start with a recap, but it's taken quite a bit. And it's good to have a recap, you know, after the break of what we were doing. And so yeah, let me emphasize this because this is a very important point. So out of this, we look at that and sec. Actually, technically speaking, we just did that when R comma C is pure. We only prove finiteness when R comma C is pure. If I'm not mistaken. We only prove, well, yeah, we only prove finiteness if the pair R comma C is pure. In general, what is finite is the set of ideals in here that are contained in sigma. Okay. But the purity just means that it's equal to R, so you will get the whole thing. Yeah. So, but this finite result is the most important thing that will follows from this existence of test ideals, if you will, that we haven't proved yet. So what else did we do? We also recall the notion of center of purity. So let me see, let's do this in order. So we work a lot on the existence of test model, on the equivalence between existence and finiteness. As a corollary, we managed to get these finite results that this set of C ideals is finite. And so I think we then saw the notion of center of purity. What was the center of purity? The center of purity was a prime ideal that was compatible. It was a C ideal, but also it is prime. In other words, it is a prime C ideal. But there is one more condition. What is the condition to be a center of purity? Such that P has to avoid the already put out by sigma. Oh, has to avoid it. So what does that mean? Actually, you solve an exercise, I hope. If not, you have to go and do it. Let's say that this variety here, or this closed subset to be more specific, is the non-F pure locus. Right? So what I'm saying here is that P has to be in the F pure locus. Let me make a whole diagram to illustrate what's happening here. So these two conditions, or this condition here, right, means that when you look at the action of the Cartier algebra, represented here by one single element, so it has to descend to P. That's the first condition. This is just a canonical coercion, and so kappa has to descend. So this diagram here represents that P is a C ideal. Just simple like that. But what is the meaning of this? It also means, well, I can go further, right? I can go and consider the field of fractions of R modulo P, and the field of fractions also goes by the name of residue field of P, right? So here, we're going to have kappa P, the residue field. So this is just localization. This is just localization. I'm sorry, people of Zoom, can you see what? Is this readable? I think so. Unless someone says anything else. So you have kappa, and something we have seen is that localization is fine. You can take kappa and you can localize it. So you don't need anything just to induce the action of the localization, because Frobenius can do localization, blah, blah, blah. So, but what is the center of purity condition? You want this map to be non-zero at the residue field. So let me reiterate. Being a C ideal means that you can go all the way to the residue field. Okay? But if the center of purity condition means that this map is not zero. Okay? If the pair were if pure, this would be non-zero automatically. Okay? But if otherwise, that's what you're looking for. Okay? And the notion of this center of purity is definitely the most important notion in the whole theory. What is the issue actually? The issue is that we don't know if they're in a form of finite sets. So we're going to make a big deal out of them. So the whole thing is that we have to cut the notion of center of purity that I'm going to call a spec. It's in a spectrum. These are just the P. P is a center of purity. For R comma C. Okay. The theorem, well, so this is the deal. If P belongs to a spec, and P is inside sigma, then this set with these two conditions is finite. This would follow straight away from what we have done so far. Because what is finite from what we have done so far is whatever is inside the crystal. This is what this is supposed to tell you. However, what is happening is that this whole thing is finite. This is the theorem. I also want to prove here finite set. Oh, sorry, see. However, its finiteness requires a more subtle type of test ideal. So this needs test ideals that are denoted like this. So this is a center of purity. I'm just denoted like this. These are the so-called test ideals along a center of purity. So, by definition, this is the smallest C ideal. In other words, ideal of R that is compatible with C. Notice that if it is compatible with C, well, it has to be compatible with the zero component of C, which is R. So it is an ideal, but also with all actions of elements in here. So smallest C ideal, not contained in E. Okay? That's the other objects we're gonna proof exists. And the existence of this is gonna be equivalent to the existence of the finiteness of centers of purity. And I want to break this out because this and this give you the whole combo. If you fully understand this test ideal and you fully understand the centers of purity, you fully understand your F-singularities. Okay? So this and that are the objects. I cannot think of two more important objects than these two to determine everything you need to know. So I guess this is the recap of what we have done so far on section 6. And so let me tell you what we're gonna do next. It took me a little bit to decide what to do next in what order. So what's next? Let me tell you the plan. So from here, what makes sense to do is some applications. To local cohomology. In particular, the famous one, it's just because I cannot just do it. It's the most important. Well, it's not the most important application, but it's one of the important applications, which is to prove that these local cohomology modules, if R is regular, I think, or regular, have finitely many associated primes. So these modules are not Euclidean. So it doesn't follow that they have finitely associated many primes, but they do. And we're going to use these finite results we've been talking about to prove that. Okay, so we're going to take a little detour to give you another nice application of the finite result of Cartier modules. Okay, that these Cartier crystals are finite, somehow manifest themselves into this finiteness.
which is striking for a lot of people. Well, I suppose it is, because these modules are huge. They're Artinian, but far from Materian. Okay? But when you consider the Frobenius action on them, then they become sort of finite enough. For this, the other thing we're going to do, and I really want to do this, is to prove the existence of test modules. This in one particular case, I want to prove that this one exists in full detail, okay? And I want to prove that, which one is the other one? Sorry, arbitrary module, but one single map exists. I'm going to put all of them, okay? So, existence. And there is one more thing. And then we're going to get back to center of purity and the so-called Cartier core map. Okay. And this is what is next. And well, then after that, we're going to come back to F regularity plus F rationality. And we're going to use all this knowledge we have acquired to give the important properties and understand how everything works. From here, I don't know if we're going to have time to study things like F signature, Liverpool multiplicity, F thresholds, which are just like numerical measures of F singularities, which are pretty cool, but I'm not sure if we're going to have the time. Because I would like to do this in detail. It's usually not part of a course somehow, or people tend to skip it because it's delicate. Mm-hmm. But we're the CMAT, right? We have to do it. So, but if we have time, then after we understand the regularity and rationality, we're gonna go to the numerics. And do we have some time for that? I'm not sure. But there are other subjects we could cover too, we'll see. But this is what we're gonna do now. I wanna give you this example, and I want to work on proving that this exists. And with that, like, I think we'll be happy, and also study the Cartier map. So now that everyone is here, I think, I wanted to do this at the beginning, though, maybe I guess we can do a little break. Since we're talking about what's gonna happen for the rest of the course. So I wanted to talk about the presentations for the end. I have some ideas of when this can happen, and I wanted to ask you if this is fine with you. So I was looking at the calendar, and the last, let me see, the last week of classes should be the week of the 21st of May. From the 21st to the 25th of May. This would be the 21st week. Is when the course is finished. So, of May, yeah. So I have here that the 21st of May, which is Friday, is the last Friday. So I wanted for you to speak or to present the material for the last week. So we would have the 23rd, which is so I have my calendar in French, so that's why I wrote this. So of May, which is a Thursday, and then we would have the 21st of May, which is a Tuesday, and then the previous one would be the 16th of May, which is a Thursday. So there are 3 students, enrolled, and I thought each of you could give a presentation in one lecture. You would have 1 hour, 20 minutes. I hope that's enough. So what I would expect is that you can just summarize the topic that you have and in that hour and a half and give as many details as you can. Would be an hour and a half good enough? If somehow any of you think, okay, I'm gonna need 3 hours, I think we can do that too. But hour and 20 minutes is fine. So this is what made sense to me. Well, I guess first I should ask if there is any day that just doesn't work for some of you. Okay, so what about you, Pedro? Would you speak any day of this?
Yeah, anyone is fine by me.
Okay, so what would make sense to me, according to the course, is that for Lorena to speak first, because the subject you're going to talk about is more the core of the course. So if that's fine with you, maybe you can speak first. So maybe that would be on the 16th of May. So Lorena is gonna tell us everything about test ideals of this form. Right? So we have already talked a little bit about the details, but it's gonna be, like the subadditivity, the discreteness of jumping numbers, this sort of things, the applications, and all that. So the point is that I told you, like, a whole bunch of people have spent their lives, studying these specific test ideals, and there are all sort of properties and wonderful things that happen that people study. So Lorena is going to give us a summary of what's going on there. And here I'm for me now, either of you makes sense going next. You want to go next? Yeah. Okay, so you might only write G. Okay, Gasolina is going to tell us about the differential side. So, for example, I told you I'm going to spend some time talking about the Cartier core map. It turns out that there is this whole differential approach in parallel that has, for example, the differential core. In particular, I suspect that one can define differential centers of purity and so on. And Gasolina is going to tell us about what's happening, like what is that picture, okay? And then I guess on the 23rd, if that's fine with you, Pedro?
Yep.
Yeah, Pedro is much easier to spell. So Pedro is going to tell us about the determinantal example. I hope. Otherwise, we can talk about a different example. So something I have noticed is that we haven't talked too much about examples. And so we're going to have a whole lecture of the most grandiose example, the determinantal ones or ring scheme variants and so on. And yeah, so I love this example because essentially Pedro is going to tell us how everything works we have done so far in one concrete but far from trivial example that it still has open problems on it. And this example is going to involve local cohomology, all sort of things that we have done so far. So Pedro is going to do that. I think this is what I have talked to every one of you, like this subject, and I think you agree on that. So if this is fine with you, then we can do this. I just wanted to get this out of the way so that we agree on this. That's good. And by the way, if there are volunteers on Zoom or that would like to present a lecture, that's fine with me too. I'm just, because we need to put some grade. So that I'm doing this officially. So, okay. By the way, I haven't updated the notes on my website because essentially I need to do it when I'm at home, and I haven't been at home for a while. So, I got here very late yesterday, so I couldn't do it last night. I just forgot. I'll do it this night, tonight. So, any questions so far? So yeah, I'm gonna update the notes. Just wanted to make sure that we have covered all the way here. Okay. Let's start. I think for the last 15 minutes we have here, let's do a little bit of this application to local homology. I think this is all due to the Vesnik. Okay. So here the notes, this will be section 6.1. Applications to local homology. For this, we're gonna fix the Cartier algebra in question to be the free one. The free one. And in particular, a Cartier module is the same thing as an R module and a Cartier operator from here to here. So remember, as part of the definition, we want this to be a finally generated R module. This is just the same thing as saying as it is in Ethereum. I don't know why people don't use this terminology more often. Instead of saying it is finally generated, it's the same thing as being Ethereum. But anyway, yeah, so if we work with this Cartier algebra, then a Cartier module is the same thing as choosing to finally generate our module. Remember that we always impose this condition for some reason. And the reason is because it's going to be a hypothesis in every single theorem. So let's just put it as part of the definition and let's save some time. So we have this. Remember that what I was saying at the beginning, another way to say this is that you have a map from here to here, but it satisfies that RPM equals R kappa M. And this is referred to as P inverse linear map. Okay. For the applications to local homology, we need to recall the dual object. This thing also goes by many different names. It's kind of annoying. People don't seem to agree on anything. So dual to this, we have the notion of F module. An F module is going to be an R module and we're going to have a map I'm going to call phi that goes from here to here. Okay. However, people, instead of phi, you will see if you open essentially many books, people are going to denote it as a map from here to here. But instead of being P inverse linear, it's going to be P linear. So it means that it is additive. The additivity is always there. So, but the R linear action is different, right? Like, so here you're going to have our PFM. So people call this a Frobenius action. It's like if M had a Frobenius embedded to it.
Okay, and it's just dual to that. These two things are the same, right? It's just a, yeah. So this is an F module, and I think that if we were to be truly honest here, we should put as part of the definition that it is Artinian. But no one does it. So, but to be symmetrical, we should put here Artinian. It's sort of this dual notion. So what are examples? Well, I'll tell you in a sec what they are. But an example is, well, R itself has a frobenius, right? So in particular, essentially, well, any functor you apply to it is going to have that structure. So when you apply any cohomology module to R, well, it's going to become Artinian, and you get it for Frobenius action too. Okay, this is an F module. And what is the example we want to consider? It's the only example I've ever seen that is interesting somehow. Okay. And now matrix duality is going to take a very specific form. And it's going to become a duality between Cartier modules and F modules. So you may expect. We have already essentially observed this when we said that the Cartier operator is matrix dual to the Frobenius action on local cohomology. So now let's take, let's say, a local ring. And let's take the injective pole of the residue field. This, right? This is something we have seen before. And out of this, we construct this matrix functor, which is humming E to E. Right? And so something that we have observed before, and this was logarithmic duality, is that this functor is going to commute with Frobenius push forward. So these two things are naturally isomorphic. What does this mean? It means that if you have a Cartier module and you apply duality, what does it become? It becomes D of M. And now when you apply it here, you get that. So a Cartier module, when you apply matrix duality, becomes an F module. Okay? And so matrix duality, at the end of the day, it's going to become this. Matrix duality let's say between Cartier modules and F modules. Frobenius modules, let's say.
So, but for this, for the duality to really work, we need to assume that this is complete. Right? And so here, we're going to have the category of Cartier modules. Remember that here we assume that C is this free-Cartier algebra of generated by one single thing. It's principal and free. Sorry. And so remember that Cartier already has the Noetherian part in it, right? You remember that Malthus duality was between Noetherian modules and Artinian modules, right? So here the Cartier already has the Noetherian part in it. And so we're gonna go, well, it depends if we define the modules of the Artinian or not. I really would like to do that, but just to emphasize, I'm gonna say Artinian F modules. Okay. So you have D, you can come back. And this is an anti-equivalence of categories. Okay. And so and as a corollary, we obtained a pretty striking result. So now we have that there is this Cartier crystals here. We could also form the Cartier crystal here, and we're going to do that, and that's going to be these Dubesnik's F modules. Okay? And so you get the corresponding equivalence. Because the nilpotent here is going to correspond to the nilpotent there. Right? And so for now, let's say at the very least we get the following, and that's the application I'm going to end up with. And we're going to keep exploring this on Thursday. I'm going to write it down like this. ENF module then if you look at the kernel of these things, this is stabilized. So you remember how we proved that if you have a Cartier module and you take the sequence of images, when you iterate that operator, this is stabilized, right? Well, now it's manifest in this in terms of F modules. Image becomes kernel. Okay, so you have this. If you have any sequence in general of F modules, well, you can say this eventually, well, this lives inside M. M has no reason to be Noetherian. So you cannot say that this stabilizes. If you assume that Ioannidis would do, then the other side stabilizes, right? Well, this part, so sequence of F submodules so eventually has, you may want to say that it stabilizes that the co-kernels are zero, the portions are zero, right? But you cannot say that. What you can say is that they are nilpotent. So eventually has F nilpotent quotients. So if you localize the F nilpotent submodules, then it truly stabilizes. And that's what we did. So we're gonna do next time to do this linguistic thing. And one that I use a lot in practice. See, up to nilpotency. M has only finally many F submodules. You have a bit of time. And so as a corollary, we obtain the following things that are exercises, but generally corollaries and beautiful things like this. So if you have a local ring that is Cohen-Macaulay and S injective, meaning if nilpotent things don't exist, then the top local cohomology has only finally many F submodules. When it has none, that is none that is non-trivial, then you say that the ring is F-rational. There is a much more general result that it was a big deal when it first appeared. Another exercise that I'm going to ask you to do. But again, this is just a corollary of that. If you have a ring that is F split, F pure, let's say, plus quasi-Gorenstein. I don't think I have defined this before, but let me do it right now. Quasi-Gorenstein means that the top local cohomology is just the residue field. So therefore Gorenstein means quasi-Gorenstein plus Cohen-Macaulay. Okay. So quasi-Gorenstein is just Gorenstein, but without the Cohen-Macaulay hypothesis. Sorry, people of my case. Removing this, and so out of this you get another standard application, which is that then the top local cohomology has finally many F submodules. And you see, local cohomology seems to be a very finite object when the Frobenius action is considered. They're huge, but if Frobenius is taken care of, if you use Frobenius, they start to look like finite things. And next time we're going to see how you can use this to prove that local cohomology have this finally many associated primes. But yeah, see, I'm gonna stop here. I don't know, any questions so far? So just to recap, next time we're gonna finish this application that I wanted to give. And then we're gonna start the existence of test ideals. And specifically the existence of test elements that I've been claiming is, like, morally speaking, resolution of singularities. This whole business. So if there are no questions, goodbye, people of Zoom.
Thanks. Bye-bye.
Bye-bye.